Okay, so now we're going to talk some more about solving linear equations. So we're going to talk about solving a matrix equation AX is equal to B, and just to remind everybody some notation and such, here's a typical example. If you had a 3 by 2 matrix equation, it might look like this, which is shorthand for the three equations: x plus 2y is equal to 1, x plus y is equal to 0, and 2x plus 3y is equal to 1. So that is to say, three equations and two unknowns. All right. And we talked about solving this by putting it into row echelon form. And so what we said is that you take this augmented matrix A, B, and then you apply row operations to replace it with a new pair, A prime, B prime, where A prime is in row echelon form. So that is to say, A prime looks like this. It has a staircase and some non-zero pivots and some zeros below, and I don't care what's above. All right, and last time I talked about how you can get any matrix into row echelon form, and a little bit about what it looks like to solve them, and so I'm going to talk a little bit more about the solving part today. So let's assume you've already done Gaussian elimination and you have an equation AX is equal to B, where A is in row echelon form. All right. So here are the basic facts about what the solutions of such an equation look like. I've already talked about these, but I'm going to talk say a little bit more detail. So the first thing, of course, is that there may not be any solutions at all. This equation may have no solutions. Okay, well, so be it. There are actually two basic subcases. If B is 0, the 0 vector, then of course this has a solution, which is to say x is equal to 0. At least one solution, x is equal to 0. And that's an important special case. So that's called the homogeneous equation, or this is the homogeneous case. And the point being, in a homogeneous equation, you're guaranteed to have at least one solution. On the other hand, if B is not the 0 vector, then you may or may not have a non-zero solution, and there's not, in general, any way to tell except to look and see. And on the other hand, let's say you've already determined that you do have at least one solution. Then what? Well, then there's a family of solutions, and the number of parameters in the family is the number of free variables in the row echelon matrix. So if there are no free variables, there's a unique solution, but otherwise there's infinitely many solutions. Okay, so as I said, we've already sort of seen this, but I want to talk in more detail about it and do a few examples. So let's see this in a little bit more detail. So let's say we have this equation AX is equal to B, and I want to spell out a little bit about A. So A is an m by n matrix, meaning it has m equations and n variables. And it's in row echelon form, so let's write it out. In row echelon form, you have a bunch of 0 rows at the bottom. I mean, there might not be any, but you typically have some rows of zeros at the bottom, and then you have the pivots, which are these non-zero guys up here. And you have R non-zero rows, and then these are the pivot variables. You have R pivot variables, and R is, of course, the rank of the matrix. And since you have R non-zero rows and M total number of rows, the number of 0 rows is M minus R. And that is to say, this is the number of equations where the left-hand side of the equation is all zeros. This is not the augmented matrix. The right-hand side of the equation, the B, is whatever it is. So you have m minus r of these guys. And since you have r pivot variables and n variables total, the number of free variables is n minus r. So these three numbers play an important role here. N minus r, the number of free variables, m minus r, the number of zero equations, and of course r, the rank. Okay, so let's look at a simple example. Suppose you had the following 3 by 3 system. Looks like this. So this matrix is in row echelon form. There are 3 variables, and suppose this was the equation. Well, let's see. Here's the row echelon form. It has one row of zeros at the bottom, and since there's zeros on the left here and there's not a matching zero on the right, this has no solutions. That's the easy no solutions test once it's in row echelon form. And just to see why that is, remember this is really the following 3 equations. The first equation is this, and the second equation is this, and the third equation is 0 plus 0 plus 0 is equal to 1, which doesn't have any solutions in any universe that I know of. Okay, so let's tweak the example a little bit and say that the matrix, the left-hand side, was the same, but suppose on the right-hand side you did have a 0 in the last place. Then what happens? Then this does have at least one solution, and here's the row echelon form, so let's check what all these numbers are. The rank is equal to 2. There are 2 pivot variables. Rank is 2. And that means there are 2 pivot variables and 1 free variable, which in this case is z. And that is to say there's a 1 parameter family of solutions. And let's just write it down. Let's see. Well, the last equation is 0 is equal to 0, which says that z can be anything. And the previous equation, working backwards, says 4y plus 5z is equal to 2, which you write as y is equal to 1/4 2 minus 5z. And that's a good thing to do because you've moved the z, which is the free variable, to the right-hand side, and you now have y in terms of z. And then finally you have x plus 2y plus 3z is equal to 1. And you bring the y and the z to the other side to write x is equal to 1 minus 2y minus 3z. And the z is fine, that's the free variable. Y is not, but we've already solved for y in terms of z. That's right here, so we plug that in to get that x is equal to 1 minus 2 times 1/4 2 minus 5z minus 3z. And now you can see on the right-hand side of this equation there are just constants and z's. And you simplify it, and it turns out that x turns out to equal minus 1/2 z. So that's it. You've solved this system. You found the general solution. Z is anything y and x are expressed in terms of z. So you can write this, the general solution in shorthand. X is minus 1/2 z, y is 1/4 2 minus 5z, and the last coordinate is z. Can be anything. That's all of the solutions. Okay, so that's the basic picture. Let's look at a couple more types of examples. So suppose we had a homogeneous equation, ax is equal to 0. And if A is m by n and rank r, then how many solutions does it have? Well, the number of free variables is the total number of variables. all variables minus the pivot variables, of which there are r. And the total number of variables, of course, is n. So this has n minus r free variables, and since it's homogeneous, it's guaranteed to have a solution, which is to say x is equal to 0. And I'll remind you, this is the n vector of zeros. And there's an n minus r parameter family of solutions. Okay, so that's an easy basic case. Let's look at the following example. Suppose I had a matrix which is a full rank. The rank is equal to m. So A is an m by n matrix, and the rank is the number of linearly independent rows, which is at most m, of course. So the maximum it can be is m. That's why I call this maximum rank. So if you put this in row, what's the row echelon form of this matrix going to look like? Well, a typical example is the pivot variables all come first, and the free variables all come last. That's not necessarily the case. They could be mixed up, but this is one of the things that can happen. And so the staircase looks like this. And then what do you know about the solutions to this thing? Well, let's write it out. You have x1 down to xn, and then b is an m vector, b1 down to bm. Does this have any solutions? Well, there are no 0 equals non-zero problems arising here. The answer is yes. The way you solve it is you do the very last row, and the very last row, the equation that you get is am times xm plus something times xm plus 1, and so on. It's not x. I don't care what you call it. It's just a bunch of coefficients times these last variables xm plus 1 to xn, and that's all equal to bm. In other words, xm is equal to bm minus a linear combination of these free variables, something times xm plus 1 up to dot 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 something times xn, and that's the free variables, and that is a legitimate solution for xm, and you can work back one step at a time. You can do back substitution and solve this. So yes, it has a solution. And how many solutions does it have? Well, how many free variables does it have? That's this number n minus m, because n is the number of variables, and m is the number of rows. Well, the point here is that the rank is m. So remember, the number of free variables is n minus r, where r is the rank. And this is a case where the rank is equal to m. And that's these n minus m variables out here. So that's a pretty straightforward case also. All right, here's another example. Suppose A was in fact an n by n matrix, and it was of maximal rank. The rank was equal to n. So it's the preceding case specialized to the case when A is square. So then the row echelon form of the thing really is A1 through AN down the diagonal, and it's upper triangular. And these AIs are all, of course, assumed to be non-zero. And if you look at this equation like this, how many solutions does it have? Well, I just said it has at least one. It's a special case of what was on the previous slide, where n minus m is equal to 0. So and the number that says that the number of free variables is actually 0, so there's exactly one solution. This has a unique solution. And this is something we've seen before. This is exactly the situation where A, it's an n by n matrix, and it's invertible. We've seen this before. And when A is invertible, the solution to AX is equal to B is given by X is equal to A inverse B, and there's only one such thing, so it's unique. So we've recaptured what we discussed a few days ago in this case. All right, I think that's a good place to stop.